Good morning, everyone. My name is Edoardo, and today I'll talk about underactuated cable-driven parallel robots and how we can exploit or control their natural free motion. My presentation starts with an introduction on what an underactuated cable robot is, and I'll give some details about their free motion modeling and present some ways to control the end effector free motion or to exploit this feature. In the end, an outlook on some current work is outlined. Cable robots are parallel architecture manipulators that move an end effector in space through extendable cables instead of rigid links. Among their advantages, they can be easily reconfigured. Their workspace can be scaled up to several cubic meters, and they can achieve considerable speed and accelerations. Unfortunately, since cables can only pull, their end effector is typically redundantly actuated and constrained. Underactuated cable robots employ end cables which are less than the end effector degrees of freedom, typically 6, and rely on gravity to maintain cables taut. Their design is simplified and workspace accessibility enhanced. But less cables also means less controllability of the end effector, whose pose depends on both kinematics and mechanical equilibrium relations. In addition, less cables also means less constrainability, thus arbitrary forces cannot be balanced and may excite large oscillatory motions. The geometry of the manipulator is described by n less than 6 loop closure equations due to cable connecting the end effector with a frame. As a consequence of underactuation, the forward kinematic problem is indeterminate. N geometrical relations are not sufficient to determine the end effector pose, and mechanical equilibrium is to be taken into account. Differential kinematics highlight a second key feature. The system Jacobian matrix is at most rank n, thus an infinity of uncontrolled rigid body motion are instantaneously possible, even if cable speed is assigned. The end effector is thus characterized by a controlled motion due to cable actuation, and by a free motion that can be modeled through the Jacobian null space, but whose causes are to be determined. The third feature of underactuated system, which derives from their under-constrained nature, is possessing an internal dynamics. This is a differential correlation between end effector coordinates independent from the constraint or control actions, and is obtained by projecting the end effector dynamics onto the Jacobian null space. In case cables are not varying their length, the internal dynamics establishes the causes of the end effector free motion, and it's called free motion internal dynamics. A way to control the free motion in open loop is to carefully plan the end effector trajectory in advance. Two approaches were considered, which can be used in different scenarios: input shaping of a nominal trajectory and rest-to-rest planning. Input shaping is a simple method which requires the knowledge of natural oscillation frequencies, but can be used in real time to partially eliminate residual oscillation in a specified bandwidth. The most notable drawback of this approach is that it works only for linear geometric paths, and oscillations are never fully eliminated. Rest-to-rest trajectories has complementary characteristics, since it allows to nominally eliminate residual oscillation from an arbitrary geometry of the path to follow, but requires a complex numerical method to be solved offline only, and model parameters need to be perfectly known. The results clearly show that, with respect to a nominal trajectory, oscillations are completely eliminated or partially present due to unmodeled effects, such as actual vibration due to high acceleration. But oscillatory free motion can also be exploited for something useful. Identification and validation of robot parameters was considered. These parameters were natural oscillation frequencies, which are needed for input shaping, and end effector inertial parameters, which are needed for rest-to-rest planning. Natural oscillation frequencies were determined by linearizing the end effector free motion internal dynamics and studying the associated Eigen problem, and were experimentally reconstructed for 2, 3, and 4 cable robots, showing a remarkable correspondence with the model. End effector inertial parameters were experimentally computed by developing a novel free motion internal dynamics identification model, which does not require force and torque measurement and only needs to record free coordinates, which are sampled over free motion trajectories. Experimental identification results show that the new model performs more than satisfactorily, since it's able to determine end effector essential parameters with high accuracy. We are currently working toward feedback control. A way to achieve it in practice is still to be determined, even though theoretical results were presented. This is mainly due to difficulties in measuring the end effector state in real time, since the robot is underactuated. Ultimately, geometry and initial pose calibration are being investigated through free motion. This approach should reduce calibration equipment cost and time. This is my end, and thank you.